Welcome to lecture 4 of scaling section of our software architecture and design course. And in this lecture, we are going to talk about auto scaling in cloud environments, right? So this lecture is about one of the most powerful capabilities of cloud computing, the ability to automatically grow and shrink your infrastructures, in response to real world demand. So before cloud computing, scaling meant that buying hardware months in advance and hoping you guessed the traffic correctly. You paid for peak capacity 24/7, even when traffic was at 5% of peak, right? So auto scaling changes this entirely. You define rules like if CPU stays above 70% for 5 minutes, add a server. And if CPU drops below 20% for 10 minutes, so then remove a server. The cloud does the rest. So this lecture covers the mechanics, the strategies, the metrics, and crucially, the failure modes that bite people in production. So let's get into it. Dear students, let me make the business case for auto scaling crystal clear, right? So look at the traffic chart over here. This is a real pattern you see in most web applications. At 2 a.m., we have only 200 requests per second. At 2 p.m. we have 4,200 requests per second, right? Since 2 p.m. is peak work hours, so you have increased number of requests per second, and that's huge difference, right? That's almost 20:1. So if you do not use auto scaling, what is going to happen? You have to buy enough servers to handle your peak hours. But those servers sit at 5% utilization at 2 a.m. So you are paying for 20 servers 24 hours a day, and that's waste. And you still crash during unexpected viral moments because you over provisioned for normal peak, but not for the tweet from a celebrity that sends 10 times traffic to your website. And with auto scaling at 2 a.m., you are running only 2 servers and they handle the light traffic easily. As traffic grows in the morning, the auto scaler scales, detects rising load and adds servers, right? So by 2 p.m., 20 servers are running. And at midnight, they scale back down to 2. So you pay only for what you use. So the cost difference, for 20 servers which are running for 24/7 versus an average of maybe 7 to 8 servers over the day, that's roughly around 60% cost reduction on computing alone, right? And the reliability is better, not worse, because unexpected spikes trigger, scale out automatically rather than crashing the fixed fleet. So this is fundamentally why cloud computing won the battle. The economics of paying per second for exactly what you need are compelling, right? Dear students, and now let's talk about the 3 main approaches for auto scaling, and you will typically use all 3 together, right? The first one is reactive scaling, and this is the most basic and most widely deployed approach. You set thresholds on a metric, typically CPU utilization, and when the metric breaches the threshold for a sustained period, the scaler adds or removes instances. And AWS auto scaling groups, GCP managed instance groups, and Kubernetes HPA all support this, right? And we will talk more about HPA later on in this lecture. And the key challenge with reactive scaling is that it reacts, right? Which means that capacity is added after load has already spiked. If your instance takes 3 minutes to boot and start serving traffic, so users experience 3 minutes of degraded performance during a sudden spike. You can mitigate this with warm pools and by keeping slightly more capacity than you strictly need. Then the second approach for auto scaling that we have is predictive scaling, right? And AWS predictive scaling was launched in 2021, and GCP's predictive auto scaling use machine learning to analyze your historical traffic patterns. If you consistently spike every Monday morning, the system learns this, and start adding capacity at 8:45 a.m. before the spike hits at 9 a.m., right? So this requires at least 2 weeks of history to learn from. Then the third approach that we have is scheduled scaling. This is the simplest and most reliable for known events. You know a product launch is happening at 10 a.m. So you know Black Friday starts at midnight. Configure a scheduled scaling action at 9:45 a.m. and scale to a minimum of 50 instances. After the event, scale back down. This is always used for major planned events, even when reactive and predictive scaling are in place, right? So the best practice is use all three approaches. Schedule for known events, predictive for recurring patterns, reactive as the safety net for the unexpected, right? Dear students, choosing the right metric to scale on is just as important as the scaling logic itself, right? And let me rank the common options that we have. So the first one is CPU utilization. This is the default metric and often a fine choice for compute-bound workloads. If your application is doing real computation like image processing, data transformation, machine learning, inference, so CPU is a good proxy for load. Scale out when average CPU across your fleet stays above 60 to 70% for 5 minutes, and scale in when it drops below 20 to 25%. The problem with CPU utilization metric is that it does not capture input-output bound workloads. For example, if your service is waiting on a slow database query, CPU might be at 5% while users are waiting 10 seconds for responses. So you would never scale out based on CPU alone. The system looks healthy, but users are suffering. Then the second, scaling metric that we have is request rate or connections, right? So scaling on the number of incoming requests per second or the number of concurrent connections at your load balancer, it's more directly tied to user experience. An AWS application load balancer has a native target tracking for request count per target. So you can say keep each instance handling at most 1000 requests per minute, and the scaler does the math and add or remove instances automatically, right? Then the third metric that we have is queue depth. So for async worker architecture, this is the best metric. If you have SQS, which stands for simple queue service, so it is a service provided by Amazon web services that temporarily stores tasks or messages until another program processes them, right? So the scaler works based on queue depth. If there are 0 messages in queue, so we require 0 workers. If there are 10,000 messages in queue, so then we have to add more workers fast. This is the most responsive because the metric directly represents work waiting to be done. Then the fourth scaling metric that we have is custom metrics. For mature applications, you can emit business metrics and scale on those, right? Like Netflix scales based on streaming request, not CPU. This takes instrumentation work but gives the most precise scaling signal, right? Dear students, scale in is where most auto-scaling bugs live. And let me walk through the 4 classic pitfalls. Number first, killing instances with active requests. And when your autoscaler decides to remove an instance, it terminates it immediately. But that instance might be handling 50 active requests. So those requests fail with a 502 or connection reset error. And the solution to this is connection draining. Like before terminating, deregister the instance from load balancer, right? So the load balancer stops routing new requests to it and lets existing request finish. And you can set a deregistration delay of 30 to 300 seconds depending on your typical request duration, right? So the deregistration delay is the amount of time the load balancer waits before completely disconnecting that server. So during this waiting period, the server does not receive any new request, but it is allowed to finish processing the request it already has. During this waiting period, the server does not receive any new requests, but it is allowed to finish processing the request it has already has. The remaining servers are now at 65% CPU and your scale in threshold is 60%. So they are above the scale in trigger but below the scale out trigger, right? But if a small traffic uptick pushes them to 72%, so you scale out and then traffic drops, so you scale in, scale out, and scale in. This wastes money and causes instability. And the solution to this is to keep a large gap between scale out and scale in thresholds, right? Like scale out should be at 70% and scale in should be at 30%. And use cool down periods to prevent rapid back and forth, scaling. And then the third pitfall that we have is stateful instances. If your app servers store session data and memory or write uploaded files to local disk, so you cannot safely scale them in. Killing the instance kills the data, and the solution is a foundational cloud principle, which is that make your app servers stateless. And sessions go in Redis or Elastic Cache, file uploads go to S3, and database state goes to RDS. Then any instance can be killed at any time without losing user data. Number 4, minimum instance count of 0. Setting min to 0 is tempting for cost savings, but it is dangerous. If all instances scale in, the next request arrives to find 0 capacity and has to wait for cold start. What is a cold start? A cold start happens when no server or application instance is currently running, and a new one must be started before it can handle a user's request, right? It's like a pizza shop. If the oven is already hot, pizza can be cooked immediately. But if the oven is completely off, so you first have to turn it on and wait for it to heat up, and then that waiting time is like a cold start. So similarly, in cloud computing, a warm instance means a server is already running and can handle requests instantly, and cold start means that no server is running, so the cloud provider has to create a new server, load the application, connect the database, etc. So this can take 60 to 300 seconds. So always keep min equals to 2 or 3, so that your server is always running and you can ensure high availability. Dear students, if you are using Kubernetes, which is basically a system that automatically manages and organizes containers, and in Kubernetes, auto-scaling works at 3 distinct layers. And we are going to talk about each of them in more details, right? So the first one is horizontal pod autoscaler, which is sometimes called HPA, right? And HPA stands for horizontal pod autoscaler. This is what most people think of first. HPA watches, a metric and adjusts the number of running pod replicas for a deployment, right? So it sets target CPU to 50%, and then if average CPU across all pods exceeds 50%, so HPA adds more pods. And if it drops well below, so HPA removes pods. Scale happens, in seconds to minutes, right? And then the second layer that we have is cluster autoscaler, which is, CA. HPA adds, pods. That is something which we already covered, but pods need nodes, physical machines to run on, right? When there are not enough nodes, pods enter a pending state. The cluster autoscaler watches for pending pods and asks cloud provider to add new nodes to the cluster, right? And new nodes take around 1 to 3 minutes to boot and to join the cluster and become schedulable. So these two systems chain together like traffic spike. So HPA adds pods and pods goes to pending state, and then CA adds nodes, then pods are scheduled, right? Then the third layer that we have is vertical pod autoscaler, which is VPA. So instead of adding more pods, VPA makes existing pods bigger, like adding more CPU, more RAM. So it observes actual resource usage over time and recommends or automatically adjust CPU and memory requests. Use VPA and recommendation only mode first, and automate requires port restart to apply new resource limits. I'd like to talk about the KEDA, which deserves special mention. KEDA stands for Kubernetes Event Driven Autoscaling, which is an open source project that extends HPA to support 50 plus event sources as a scaling triggers, such as Kafka consumer lag, SQS queue depth, Azure service bus, Redis list length, even HTTP request rate. So if you're using Kubernetes with async workloads, Keda is the tool. Dear students, now let's talk about 6 proven best practices for auto scaling, right? So the first one is test scale in as carefully as you test scale out. This is something which I've seen a lot, that almost every team runs load test to make sure that system can add more servers when traffic increases, but very few teams test what happens when servers are removed while the system is still busy. So you can add this to your testing plan, and during normal traffic, purposely shut down about 50% of your running servers and make sure users do not experience any errors or failed requests. Number 2, use warm pools. A new EC2 server, usually takes around 3 to 5 minutes to start to load the application and become ready to handle users, right? So during a sudden traffic spike, waiting 3 to 5 minutes is too long, and users may start seeing errors. So AWS warm pools solve this problem by keeping pre-configured servers ready in a stopped state, right? So when needed, they can start it in only 15 to 30 seconds, which is much faster. Number 3, make sure your health checks test the real health of the application, right? The autoscaler removes servers that fail health checks, right? But if your health check only returns a simple OK message without checking important things like the database connections, cache, or available worker threads, so then unhealthy servers may continue receiving user requests. So a good health check should confirm that the application can actually serve users correctly. Number 4, monitor your autoscaler itself. Do not only monitor your application, also monitor the auto-scaling system. If it reaches the maximum number of servers and cannot add more because of capacity limits, permission problems, or lack of available network resources, so you should know immediately. Set alerts for failed scale outs and long periods at maximum capacity and servers that remain stuck in the pending state. Number 5, scale out quickly but scale in slowly. It is better to add servers fast and remove them carefully. If you accidentally run a few extra servers, the result is only slightly higher cloud bill. But if you do not add servers quickly enough, users may experience slow responses or errors, because underscaling hurts users. So your auto scaling policy should always be more aggressive when adding capacity than when removing it, right? And number 6, your application should be stateless, right? So this is one of the most important rules for successful auto scaling. No single server should store important data that cannot be replaced. Any server should be able to stop or fail at any time without affecting the system. If an instance keeps unique or irreplaceable information, then removing or replacing that instance becomes risky, and your auto-scaling setup will not be reliable. Dear students, before we conclude this lecture, here are 5 things to take away from this lecture. Number 1, auto-scaling is fundamentally about economics. Converting fixed infrastructure to variable cost is one of the highest ROI, return on investment, things that you can do as a platform engineer, right? So most teams see 40 to 70% compute cost reduction. Number 2, use all 3 scaling types together. Reactive scaling catches the unexpected situations, and predictive scaling handles reoccurring, and schedule scaling prepares for the known. So they are complementary tools, not alternatives. Number 3, the metric you scale on determines the quality of your scaling decisions. So match the metric to the workload type. The wrong metric either scales too late or thrashes. Number 4, Scale in has more failure modes than scale out, right? Such as connection draining, flapping prevention, and stateless architecture, minimum instances floors. So you need to understand and configure all of these before relying on auto scaling in production. Number 5, in Kubernetes, understand all 3 layers like HPA, CA, and VPA, right? And how they chain together. Add KEDA for event-driven workloads. So this concludes this current lecture, and you have now covered the full arc from sharding strategies to read replicas to consistent hashing to auto scaling. So these are the core scaling tools for modern distributed systems, right? Use them wisely.
Thank you so much for watching this. Before you go, please don't forget to subscribe to my YouTube channel and turn on the notification bell so you never miss any of my upcoming videos. I regularly share valuable lessons, practical tips, and step-by-step tutorials to help you improve and grow. And if you are serious about mastering software design and architecture and want a complete structured learning experience, so I have created a full course that includes detailed lessons, assignments, quizzes, and downloadable workbooks to help you practice and apply what you learn. So if that sounds helpful, just check the link in the description below and enroll in the course today. I would love to see you inside and support you on your learning journey.